In this session, we'll look at how NAND gates can be used to form the most basic memory or storage device. So let's take a look at a timing diagram for a NAND gate. We can see here the symbol for the NAND gate, and we know that X, our output, is going to be low when both the inputs are high at the same time. So if we look at our two inputs, A and B, we can see that they change over the period of time that we have represented here. So what we're looking for is when they're both high at the same time. First time we're going to see that is right here for one time period, and then if we continue a little bit longer, we see another 2 time periods here where they're both high. So that means during those 3 time periods our output X is going to be low. So let's fill that in. So we have a low here and we have a low here. The rest of the time periods the output is going to be high, so we can fill those in. Probably a good idea to label this, so let's say that's A and B inverted, which is our NAND gate. And now let's take a look at that waveform. We have an active state twice, here where it's low and here where it's low. That means everything else, these 3 time frames here, these 2, and this group at the end, are all considered the resting state. So when we're looking at the NAND gate in terms of timing, we have active states and resting states. Now we're going to take a look to see what happens when we put 2 NAND gates together, and we're going to use an interesting technique called cross-coupling. And this is going to give us some unique behavior that we can use to our advantage. So in cross-coupling, what it means is we're going to take the output of one and connect it to the input of another. So here we have 2 outputs, 2 open inputs. So to cross-couple them, we're going to take Y, feed it into the input of the top NAND gate, and we're going to take X and feed it into the input of the bottom NAND gate. So you can see why it's called cross-coupling, because in the center section here we have coupling, which is the connections, and the cross because of what we're seeing here. Now, let's take a look at the top NAND gate. We can see that it has an input of A, which we've got right here, and the second input is coming from Y. So let's fill that in our truth table. And that means that X is going to be dependent on both A and Y. When A and Y are both high, our output will give it a 0. Any other time, our output X will be 1. Now if we look at the bottom NAND gate, we can see that it's dependent on an input of B and X. So let's fill that in the truth table for the second NAND gate over here. And again, we can see the normal behavior for a NAND gate. Both inputs are high, we'll get a 0 out. Any other time, we're going to get a high out. This cross-coupling of 2 NAND gates gives us a new device which is called a latch. And we're going to see that latch as we move through looking at basic memory devices. This particular latch stores 1 bit of information. That means it can store a 0 or it can store a 1. Using these, we'll be able to build all kinds of memory devices. So how does this latch actually store data? Let's take a look at what happens when our inputs A and B change over time. Remember that any time A or Y changes, that X might change. Anytime B or X changes, Y might change. So these are the two truth tables for the 2 NAND gates we have inside the latch. When we're looking at a timing diagram, it's quite common to assume that all the outputs start low and that the system will remain in that state until one of the inputs changes. So we can mark in X and Y as lows up to the point of the first change in any of our inputs, which happens along this time. Now if we look at the actual inputs, A is the first one to change, so we can see it go from high to low here. A is represented in the first truth table, so if A changes, we may have a change in X. So we've gone from high to low, so we need to look for A being low, and then we need to see what state Y is in. Well, right now, Y is low, so we have the first case here, where A is low, Y is low, which means X is going to go high. So we can mark that change in on the X waveform. But then we've had a change in X, so we need to come over to our second truth table and see what's B, what's X, and therefore is Y going to change. So B right now is high, X is high, so we're in this last row of our truth table, which means Y is going to be 0. Well, Y already is 0, so we can continue that over until we get the next change in any of our inputs. So here we have A going from low to high. So we need to go to this truth table. We need to say that A has gone to high. What's the state of Y right now? Well, Y is low. So we're in this third row. So A is high, Y is low, X is going to be a 1. Well, X already is a 1, so no changes, so we are going to continue until one of our inputs changes. The next one that happens to be is when B changes over here. So here we have B going from high to low. B affects the bottom NAND latch, or the bottom NAND gate in the latch. So B has gone low, so we're looking at one of these two cases here. X right now is high, so we're going to look at this second row where B is low, X is high, giving us an output of 1. So that means Y is going to change from low to high. Now as Y changes to high, we need to come over here and see if it affects X. So right now A is high and Y is high, so we're in the bottom row here. It says X is going to go to 0. So that change in Y has affected X, so it's going to drop down. Now the question is, does this change in X affect Y again? So we come over here. X has come to 0, and B right now is also at 0, so we're looking at the first row. Y is going to be 1. Well, it already is, so this change in X did not affect Y. So we come over to the next change in inputs, and we have a rising edge of B, so going from low to high. So B affects our second table. B has gone high. We need to know what X is. X is low right now, so our output for Y is going to be a 1. It already is, so no change with that rising edge. So we can carry our two lines over to our next transition. Now the last time we saw a pulse on A, X went high and Y was low. So let's see if that happens again. So this time A has gone low, so we're looking here. We need to know what Y is. Y is currently high. So we're down in this last row right now. Oh, sorry, we're in this middle row. A is low, Y is high, which means X goes to a 1. So X goes high as it did before. Does this change in X affect Y? Well, X has gone high. B right now is high, so we're looking at this bottom row. Y goes to 0, so it's going to drop down, so that did have an effect. Does this change in Y affect X again? So Y has dropped to low. A is currently low, so we're in the first row here. X is going to stay at 1. So that's going to continue till the next change in our inputs. We've got a rising edge here. So far, the rising edge here and here haven't had any effect. Let's see if that pattern continues. So A has gone high, so we're looking over here. Y is low right now, so we're in the third row here, and it tells us X is going to stay high. So that rising edge had no effect. So we come over to our next change in input. This time we have a falling edge on B. Last time we had a falling edge on B, we saw Y go high and X followed immediately, switching to low. Let's see if that happens. So we have B going low, So we're in this table here, and X right now is high, so we're in this second row, tells us Y is going to go high, which is what we expected. When Y goes high, we're back over here. A right now is high, so we're in this last row. X goes low. So the change in Y caused the change in X. Does this change in X cause another change in Y? Last time it didn't, but let's make sure again. So X has gone low, so we're in the first or the third row. B right now is low, so we're in this second row right now, which says Y stays high, so we'll mark that in. We go to our last transition, which is the rising edge of B. None of our rising transitions so far have caused any change. We'll verify that one more time. So B has changed to a high, so we're in the last two rows here. X is low, so we're in the third row. It tells us Y is high, so no change, and we continue that to the end. So let's take a look at what has happened in terms of our output X. So let's just focus on X right now. When A goes low, so we have a pulse of A here, and B is high, we can see X goes high, which is called a set. So this pulse in A, as long as B is in its opposite state, causes a set for our output. When B goes low, so we have a B going low here with A being high, so they're in opposite states, we can see that X goes low or is reset. Here we have another A, X is set. Here we have another B, X is reset. So we can see this is causing a set, a reset, and a reset. Now what happens in between? So in this case we have both pulses high, both inputs high here, both inputs high here, both inputs high at the end. And what happens? X maintains whatever value it had. And this is where the storage part of the latch comes in. So we can set, we can hold, or we can reset. So let's summarize what we've learned about the NAND latch. First, let's look at the NAND latch symbol shown up here in the top corner. You can see that it has two inputs, one labeled S0 for set, and the other labeled R0 for reset. The inversion bars indicate that the input is active low. The outputs are labeled Q and Q0, and as the names imply, they're the inverse of each other. So we can see down here we have the internals showing. So we have our NAND gate cross-coupled with a second NAND gate. We can see the S0 input is where we had A before. The R0 input is where we had B before. Q is what we were calling X, and Q0 is what we were calling Z. We've got the truth table here for the latch itself. Before we looked at the individual truth tables for the top and bottom NAND gates. Now we're going to complete the truth table for the latch itself. Down here we have the waveforms that we generated on the last slide. So we can see our set input, our reset input, and our output. In this case, this was what we identified as X. So we can see, looking at this output, that we have a pulse on the set input, and we can see that our output Q goes high because of that. We have a reset pulse here, and we can see that Q drops down again. We have a set, causes Q to go high. We have a reset, causes Q to go low. So let's fill those in on the truth table. So our set condition is when the set input is active, which is low, and the reset input is inactive or resting, which is high. So we want set to be low, reset to be its opposite, or high. So we're going to mark that as a set. And a set simply means the output is a 1 and that the latch is storing the bit 1. Now let's look at the reset conditions. So we have the reset input active low, and we have the set resting or high. So we have set is high, reset is active. That we're going to mark on the truth table as an R for reset, and what that means is the output Q is going to be a 0, so the latch is going to store a 0. Now, in between, when both are inactive, so we have a case here, we have a case here, again here, again here, and then a short one at the end. So in each of those cases, both S and R are inactive, so they're both in their resting state of 1. What that means is our output is going to hold whatever value it had before. So the latch is going to maintain the 1 that we had here, the 0 that we had here, the 1 that we had here, the 0 that we had here. The last case we don't have an example of on this particular graph, so let's put one in. So if, for example, set went low or active and reset also went active at the same time, we have a bit of a strange situation. So we have both active, which corresponds to this row in our truth table. And what happens here is pretty unpredictable. If we work through the waveforms, it may show that they both go high. Actually, this should just go high over here. But we're not sure. Sometimes it can fluctuate. So what we would do is we would mark any time that both our inputs are high with an X to indicate that it's unstable. So in our truth table, we're going to mark that as an X. In some cases, you might see it marked as unstable. As we'll see in the next few sessions, this latch is the basic building block for all memory elements.